Hello everyone. So today I want to talk about dependency analysis of Haskell declarations. And we'll begin by asking questions: what is even dependency analysis and why do we even need it? So in other languages like C, like Java, even some functional ones like OCaml, you have to write declarations in specific order. So for example, in C you can't call a function before you actually declare it. But as we know, in Haskell, this is not the case. In Haskell, I can write declaration wherever I want, and I can use it everywhere. So how does GHC do it? Can it just deal with things being in arbitrary order? Well, not really. In order to type check everything, GHC still needs to type check things in specific order. So, for example, parity function key here calls flip_p function. And in order to type check this function, GHC needs to know what flip_p is. It needs to know the flip_p type. That's where type checking environment comes into place. So when GHC will type check this parity function and it encounters this flip_p function here, what it will do is it will look that function up in the type checking environment. And if it's there, and it should be there, type check environment will contain like some information about flip_p's type, how many arguments it will take, and so on. So it will look that function up there and use that information. And in order to add things to the type checking environment, we need to type check them. And in order for flip_p to be already in the environment to type check parity, we need to type check flip_p before parity. So that's the job of the dependency analysis. The job of the dependency analysis is to analyze the code and order things in such a way that they would type check. And the first thing that dependency analysis does is to split type level declarations from term level declarations. Because currently, in pretty much every case, types can never depend on terms. So we cannot like use term level functions on types at the moment. If we're in the future, when we hopefully implement dependent types, this will not be the case, so this would have to change. But this is not the topic of this talk and the story, and it's a story for another day. So after splitting terms and types, it will perform an analysis on declarations there, and it will order them in order of dependency. So let's see how that works step by step. So first thing that GHC will type check is nat, and that's because nat doesn't depend on anything, and it's the first thing to come in the source code, so that's the thing that will be type checked first. After nat is type checked, nat and its constructors will be added to the type checking environment. Then GHC will type check parity because it's the second thing that comes in the source order, and parity doesn't depend on anything either. After parity is type checked, it and its constructors will be added to the type checking environment as well. Then GHC will move on to terms, and first it will type check flip_p, and that's because parity needs flip_p type checked before we type check parity. So then GHC will type check flip_p and add it to the environment, and finally we type check parity. And when we type check parity, GHC will encounter flip_p and see, aha, we have flip_p in the environment, everything is good, we know flip_p's type, and so on. And that's kind of how it works on the like bird's eye view level. We will go into more detail how exactly GHC figures out the order of dependency a little bit later. And first I want to talk about template Haskell splices. So earlier I mentioned that types can never depend on terms, but this is not entirely true because of template Haskell. For example, here I have a template Haskell function generate record, which takes a term level list, and based on the description in that list, it generates a record. So for example, we have a book, and book can have ID, title, and author, and this is the types of those things, and it will generate the record based on that. So in a way, this is a type that depends on terms, because if I change this term level list, the type will also change. So how does GC do this if it always type checks terms after types? Um, well, when analyzing a module, the first thing that GC will do is split that module into groups. And in between those groups, it will have template Haskell code. So, for example, GC will... for example, here we have two groups. We have this group here with a book description. Then we have template Haskell splice. And then we have the second group, which will have the library function and the generated book thing. And what GC will do with those groups is that it will always type check the group individually. So it will type check this group here first, and only then it will move on to analyze and type check the next group. And it won't even consider this next group when type checking this group. So groups are always type checked in order. And a side effect of that is that we can never mention things that come after a template Haskell splice. So here I use mention file format. I want to use it, but file format comes later on. And GC will actually, if you do this, GC will actually output an out of scope error, because when it will type check and analyze this group here, it doesn't know anything about this group, because it will only move on to that group after it is done with this one. So now that I mentioned this template Haskell specific, let's take a look how types are ordered. How does GC figure out the order of dependency for each type, for the type level things in each group? So here I have a bunch of declarations, and the first thing that GC will do is it will go through each of those declarations and it will make a list of names that are used in that declaration. So for example, for L here uses two names. It uses listcb and op. So those two things are the dependencies of L. After making a list for every declaration, GC will build a directed graph based on those names, where each vertex is a declaration and each edge is a dependency of that declaration. So for example, L here, this is its vertex, and the dependencies for L is listcb, you can see this edge right here, and scc. Oh, sorry, scc, and op. So, and this is the resulting graph that we have here. After building the graph, GC will try to find strongly connected components in it, or SCC for short. So, for example, so what is even a strongly connected component? A strongly connected component is, strictly speaking, it's a part of a graph where if you take any vertex of that graph, you can reach any other vertex of the same part. So for our purposes, simply speaking, it's a mutually recursive group. For example, here we have listcb and it mentions listbc, and listbc mentions listcb. So we have edge from one to another and from another to one. So they mutually depend on each other. And that's what a strongly connected component is. After finding strongly connected components, GC will just put them in the order of dependency and type check them in that order. So you can think of building strongly connected components as like building a super graph, where each vertex now is a strongly connected component, a mutually recursive group, and each edge is dependency between those groups. So for example, this group here depends on this group here because of this edge. And GC will first type check this group, and then it will type check that group. And this all works really well, but there's one quirk though, and that is type instances. The problem is that to identify our vertices, we use names. And for references, we also use names, but instances, they do not have names, right? So how do we actually account for instances in our graph? Well, GC takes a somewhat simple approach. So first, it doesn't account for them in the first pass. It just builds this sequence here. This is not a graph. This is more like a sequence, the order in which things will be type checked. So here we have a type family prop type, which is describes basically a type for a property. Then we have two properties, title and resizable. And title has type symbol and resizable has type bool. And then we have this property main window, which takes a property and outputs something that has a type of property type. So for example, main window W title outputs a string because it has a type symbol, and resizable outputs true because it has type bool, because prop type W resizable equals to bool. And if you're not familiar with this for all syntax here, it's pretty similar. It's pretty much the same as the for all dot syntax you're probably used to, except it's not implicit, it's explicit. You have to pass it as an argument. As you might know, you can pass implicit arguments with like @ symbol, but this one is explicit. It's called visible dependent quantification, if I remember that term correctly. So as we can see in the things that we've got here, after GC did already all of the dependency and like build a graph, found the strongly connected components, and we got this list of things, instances are not figuring here anywhere. So where do they go? So first thing that GC does is for each instance, it also builds a list of dependencies. So for example, prop type W title depends on three things. It depends on prop type W title and symbol. And prop type W resizable also depends on three things. It depends on prop type W resizable and bool. Since symbol and bool are imported things, they are removed from the list immediately. But afterwards, GC will go through each group and it will remove things from the list as it encounters them. And as soon as the list is empty, it will attach that instance to that group. So let's see what I mean. So first group here is prop type. And we can see we have prop type in both of the lists here. So prop type is removed. Then we move on to the next group. In the next group, we have W title in this list and nothing of interest in this list. So W title is removed from this list. This list is now empty. So this instance is inserted into this group. Then on the next group, we see that the only thing left here is W resizable, and we have W resizable here. So it will insert the instance here as well. And this algorithm is pretty good. It works most of the time. You probably have never encountered issues because of the way that this algorithm works, but it doesn't work 100% of the time, and that's exactly what we're going to talk about here. So this example is quite elaborate, but I'll try my best to explain it. We have two type families here. One of the type families is pretty simple. It's open A. It basically takes a type and returns some other type. So for example, open bool is an @ open float is a type, and open char is f float. So let's look at the f type, f signature. F is also a type family, and it takes some type and it outputs a type that has kind of open A. So for example, f bool should return something with kind open bool. And if we look at open bool is a @ and 42 is a @ So everything is correct here. Same with a float. With a float, we need to return something that has kind open float. And as we can see here, open float is a type. So we must return something that has kind type. And nat list is, in fact, a type. And fchar is a little bit more elaborate, and that's going to be the source of our problems. Spoiler alert. So fchar is, we should return something of kind open char. And if we look at open char equals to a float. And if we look at a float is a list of nats. And this is, in fact, a list of nats. So this should type check as well. This is the correctly typed code. However, if you try to put this piece of code into GC right now, you'll get this error: expected kind open char, but got a nat list. So as we've just figured out that open char does actually equal to nat list, because open char is a float and the float is a list of nats. So why doesn't GC know this? And the reason GC doesn't know this is because of this grouping here. So because of how this current algorithm works, first group will be open and two instances here that only depend on open. Open char won't be here because it also depends on f. And in the next group, the rest of the instances are inserted because all of the instances for f depend on f, and open char f float depends on f as well. So all of the instances are inserted here. And the problem here is that to know that open char equals to a float, GC should already have that instance in the type checking environment. But since they're all in the same group, they're type checked in the same time. Open char instance here is still not in the environment when we check fchar. So GC sees that we must return open char because of the signature of f. And that's it. It doesn't know what open char reduces to because there's nothing about open char in the type checking environment. And that's the problem here. This code should type check, but GC rejects this, and it rejects this because of this algorithm. And one might think like, oh, maybe inferring dependencies by name is like inferior way of doing this, because like instances don't have a name, and this dependency to open char here, it doesn't like, there's no reference to it anywhere. How could we possibly refer to this dependency? But I want to show like a little thought experiment that analysis using names is enough if you have like enough syntax to support it. Which won't be like a pleasant syntax, but it's possible. That's the point of the experiment here. So let's imagine for a moment where we have to name instances. So instance name will be starting with $, here in my fictional syntax. So for example, open bool instance is called open bool, and so on. And to actually use an instance, you have to explicitly cast it. Like you can think of this like a calling a function. Like to call a function, you have to actually write the name of the function. And the same thing is here. This pipe and arrow symbol here in our fictional syntax, it's casting using an instance. So for example, let's manually type check open char using this system. So open char should return something of kind type. But we're returning a float. And if we look at the signature for f, a float returns open float. And to see that open float equals to type, we must explicitly use open float instance for that. And now everything is correct. And the same with char here. So we must return something of kind open char. So we use open char instance to turn it into a float. And then we use a float to turn the float into nat. And if we build a graph for this system here using just name references, we get this messy graph right here. But the point of this messy graph is that actually there's no mutual recursions here going on at all. Like if you take any vertex here and walk through arrows, you'll eventually end up at open. So really, we can just type check all of these things, all of these instances in order. None of them are mutually recursive. Even if it seems so that it is mutually recursive, like, oh, but there's like f and open and so on, it's actually just the instance of open char that depends on f. Actually forgot this arrow here, but there's an arrow here to f, supposed to be an arrow. This is a complicated graph. So that's the end of the thought experiment about instance names. Obviously, we're not going to ask the programmers to name every their instance and like specifically explicitly cast them. That will be very verbose and not pleasant. So at this point, we might ask the question, but like we have these advanced languages like Agda, like Quirk or Idris, which already have dependent types even. So how do other languages solve this issue? Well, the truth is that they don't even have this issue because they, just like any other language, check things in order. So in order you write things in, that's how they will be checked in languages like Idris and Agda. And if you have mutual recursion, in Idris, for example, you have a keyword mutual to like dedicate a mutual block where in those blocks things are considered to be mutually recursive. And we could maybe do something like this in Haskell, right? Well, we obviously can't just change GC to type check everything in order. That will break a lot of code. But we could maybe like have an extension that also lets us like dedicate ordered blocks, like kind of inverse of what mutual blocks are in Idris. But this approach is considered non-Haskell-y, so we're not taking that. We're rather fix the dependency analysis so it works correctly. There is a workaround right now in GHC that kind of takes this non-Haskell approach, and that is the template Haskell splices. If you recall from earlier, template Haskell splices split the module into groups, and those groups are always step checked in that order, and each group is like individual, like each group getting type checked, all of its things added to the environment, and only then GHC moves on to the next one. So, and we can fix this code by just forcing GC to type check open char and f float first, because that's the two things we need for this to type check. And then after that, because of this splice, GC will type check this instance individually. And this code will actually type check in GC right now. So that's a workaround to the issue right now when you want to order things in specific order. But that's like inconvenient and it's like kind of hacky. So let's see what we can do with our dependency analysis. But first, let's take a look at another example. So another example is kind of similar to the first one, except there's like less type families involved and less recursion or references. So we have two type families. Xkind is a simple one. It's takes a type, returns a type. Value is a little bit more complex one. It takes a type and it returns a function from Xkind of that type into type. And then we have this data T data type, which its first parameter is just some type. And the second parameter is a function from that type into type. A lot of type words in this slide. And the constructor is irrelevant. You don't need to pay attention to that. And there are these two instances here. Like to see clearer what's going on with these instances, let's look at kinds. So this f has kind from k into type. That's because of this definition here. That's what definition of signature of data T says, that f has type of a kind of k into type. So that's what the kind that this thing has. And let's look at what kind we must return. So value says that we must return Xkind m into type. In our case, m is t. So we must return Xkind t into type. So to type check this code, we need to know that k equals to Xkind. And we do know that, right? Because of this instance here, Xkind t just returns k. So these things are equal. But again, because these instances end up being grouped together, GC doesn't know what Xkind t reduces to, and you'll get the same error where it will say that it expected Xkind t but got k, and it doesn't know that k equals to Xkind t. So what we really want here is to actually separate this into two groups. We want to somehow show that there is a dependency between these two things, because we have one instance depending on another one. And that's where the sig and def notation comes in. The original idea for this split that we're about to do here was proposed by Richard Eisenberg in one of the tickets. And then Simon Peyton-Jones kind of refined that idea into the notation we have here. So the idea behind sig and def notation is that sometimes to type check things, you don't need to actually know the entire declaration. So for example, here we have type instance bool, fbool, and to type check this type instance, we don't really need to know what type what constructors of bool are. Like we only care about bool's kind. We only care that that kind is type to type check this. We don't care that bool has true or false. Maybe it has nothing. Like maybe that's how it's defined. We don't care about that. So really, this instance here shouldn't depend on the entire declaration. It only cares about this little part here that says that bool actually has kind of type. It doesn't say that explicitly, but GC will infer that. So the idea is to split signatures and definitions, so we have more granular control over what things depend on what. And you can think of a signature as a left-hand side of a declaration, and you can think of a definition as a right-hand side of a declaration. So in this example here, we have data bool is the signature and true and false is the definition. And for the open type family here, the type family declaration is signature, and all of its instances are considered a part of the same definition. So they're all grouped together. I'll touch on that later because the part that they're all grouped together is important. So now we need new rules for, actually before we need new rules, we need a new graph. So actually we changed our graph now, directed graph, to before we had vertices that are declarations. Now we have vertices that have two types. One of them is signatures and the other one is definitions, or sig and def for short. And we need new rules. Before we only had one rule really, where like, oh, if we encountered a reference to something, we add an edge to that name. But now that won't work because we actually have like two things that have the same name. We have fsig and fdef, and they're both f. So we need new rules. And the first rule is every def depends on its corresponding sig. The reason for that is simple. To type check a definition, we need to know the signature. So every definition will depend on its corresponding signature. That's a pretty simple rule. The second rule, if we mention a name like bool here, a type level name, we add an edge towards a sig of that name. So as I said before, to type check this instance, we don't need to know the definition of bool, we only need to know the signature. So we add an edge only to the signature. And the third rule is regarding data kinds. So when you refer to a promoted data constructor, you actually depend on a def, because now I mentioned false here, and false is actually a part of bool definition. So this instance here depends on bool definition and not the signature. And transitively, it also depends on the signature because every def depends on its corresponding sig. So that's the third rule. And that's the graph we get here with dependencies. Fdef depends on two things, and fsig, and bool def just depends on bool sig. And we need an extra fourth rule, which is somewhat a sneaky one. So if we look at this data type here, it's a pretty simple one. It's data TA, and the data constructor is make TA. It's trivial. And the sig part is this part, and the constructor is the def part. And let's look at what GHC will do if we actually split it into sigs and defs, and they end up in different groups. And by that I mean GHC will type check the signature first, and then in some later group it will type check the definition. So looking at the signature here, GHC doesn't know what definition is yet because it just has the signature. And it will, since this type doesn't have any like specific kinds supplied by the user, it will try to infer the kind. And it will try to infer the most general kind possible. And the most general kind possible for the signature is for all k into type. And if we actually go to the definition, and once GC gets to type checking the definition, you'll get a type error because we have this data constructor here, and data constructors accept variables to have kind type. But we inferred that A doesn't have kind type. We inferred that it has type K, which can be anything. So we have this conflict here where actually this declaration meant this A to be type, but because we type checked the signature by itself without considering the definition, it was inferred to be just some K. And to fix this little issue, we need to make sure that definition, in cases where the kind is not supplied by the user, like via a standalone kind signature, for example, we need to make sure that these two things actually end up in the same group. And to do that, we add this little extra edge here from sig to def. And now these two things are mutually recursive. So they will always end up in the same group because they will always be a strongly connected component. Now let's take a look at the piece of code that doesn't compile now. It's not like a full code, but the idea will be the same. So this piece of code, I will not go in detail what it does, but I will go in detail what dependency analysis does to it right now and how does it work with the new system I've just described. So currently, dependency analysis just looks at names, right? So if we look at this data U here, it mentions L, and this type family L mentions U in its kind signature. So as far as GC is concerned right now, these two things are mutually recursive. They reference each other. And if you try to compile this code and like you insert any here or some real implementation or whatever, you'll get this error that the type constructor cannot be used in kind when it's part of the same recursive group. And with our new system, since SIGs and defs are separated, we can actually look at, we can actually see that these things are not mutually recursive. So let's take a look at U here. U is the first thing. So USIG is actually super simple. It doesn't depend on anything. It's just a type. It's a thing by itself. Then let's take a look at the LSIG. So LSIG depends on USIG because it mentions U, but it doesn't need the U definition because it doesn't refer to any data constructors. The signature of L just refers to U, so it only cares about this little part right here. Now let's look at UDEF. UDEF mentions L here, so it needs L's signature to type check, but it doesn't need the definition, just need the signature. So it has two edges going towards the corresponding SIG, which is our first rule, and towards the LSIG, which is our second rule. Now let's look at the LDEF here. LDEF here depends on the corresponding SIG, and then it actually mentions a data constructor from U. So it also depends on UDEF. And if we like look at this graph, there's no like loops here. We can just type check this entire thing in order. We can type check signature of U first, then signature of L, then definition of U, and then definition of L. So that's a kind of control that this new system allows us to have. We can draw this extra edges here and type check things in more precise order. So let's look at our, actually, yeah, that's the graph. Let's look at our Xkind example from before. So type family declarations here are just signatures, and then we have this data T here, which is a signature and a definition. And then we have two instances, which are Xkind def and value def. And this is the graph we get here because value mentions Xkind, this edge here, and both of the instances mention T, so they both depend on T. And if we look closely at this graph and recall what our problem was that we really wanted to type check Xkind before value in order to have Xkind T instance in the environment before we type check value. But the problem is that there's no dependency here between these two things. So what we really want this little extra edge here. And the question how to, so the current four rules are not enough to infer this edge here, as we can see, right? Because this graph is built according to all of the rules I've laid down, and this edge is not here, but we want it, we need it. So the question now becomes is, what exactly set of rules we must use to infer this edge and infer enough edges so everything type checks, and not infer like in any unnecessary edges, because that can also lead to some code that doesn't type check. And the exact set of rules is still kind of an open research question. There have been the original set of rules proposed by Richard, and we've tried it, and we figured out that it doesn't always infer all of the edges we need, and sometimes it infers unnecessary edges. And several other set of rules have been proposed since, but we haven't had the chance to try them yet because of the more pressing issue. And that more pressing issue is the type checker. So in this simple little code here, we have a little bit of an interesting thing going on, which is kind of core to our idea. So we have a type signature for T, and we have a definition for T coming later. And we have as data type E, which uses T. That's important. So when GC actually combines these things into groups and starts to type checking them, it will type check this part just fine. But then on this part, we see we reference T here. And ideally, we only need this part here to type check this. But the way the type checker is built at the moment is that if you try to do that, if you try to use a signature and the definition wasn't type checked yet, GC will crash, type checker will crash. And apparently to fix this little problem here requires quite a big refactoring of the type checker. You need to untangle some things. And yeah, so that's why the current state of dependency analysis is that we have this idea. We have possibly a working set of rules to implement it, but we have this big roadblock here, which requires some major refactorings. And that's what we're currently working on. So, and that's all I have for dependency analysis. Do you guys have any questions?
I'll try to read the chat here. Does visible for all quantification exist in GHC already? Yes, it does. Ryan actually already answered that. Yes, you can't have another question is that at the type level, you can use visible for all quantification, but you can't use it at the term level. Yes, you can't, but there's a proposal for that. And I think it's under review right now. Is this the lambda cube I've heard so much about? I've also heard a lot of lambda cube, but I'm not aware if this is the lambda cube. I'm not that sophisticated in my lambda cube knowledge yet. So another thing was probably correction to my slide. So someone asks, should it be xkind tkf into this thing should have like two type variables? Yes, it should. I forgot to add them, and it should be that like that here. Question, why do we need to figure out dependency graph ahead of time? Could we conceptually type check all of the definitions concurrently, blocking if we hit a dependency that isn't yet type checked? I mean, that's somewhat what happens with mutually recursive definitions. So if you're familiar with a function called fix, which allows you to have like self-referring things, to resolve mutually recursive declarations, you need, that's what GHC does. It puts like empty holes, empty holes for things that should be type checked, and it type checks them and fills those holes like as it type checks them. And when it does type check mutually recursive declarations, in order to type check them, it actually type checks the signatures first, and then it type checks the definitions, so it doesn't loop itself. And that's why in that example here, there it is. There's my example. That's why in this example here, it says that we cannot use u here because we use u in the L signature, but u is its own signature. So we must have u type checked before, because those signatures are type checked at the same time, and we cannot reference u here because of that, because it is mentioned in the signature. But like, I'm not sure if if the entire compiler could work like that, like can type check things concurrently. I'm not sure. Question, what happens to the part of the same recursive group error message seen in LPy example in the new algorithm? Can it still happen under certain circumstances? I don't think it can. Like the only way, so the problem with this thing was that since we type check both signatures at the same time, but this signature actually requires this signature to be type checked, that's why we get this error here, right? Because we type check them at the same time. We have to type check the signatures first. But here, for that to happen, we need to somehow have have a signature that is type checked at the same time as the definitions. But since every def depends on a sig, I don't think that's possible, but maybe it is. Again, it's like many of these things are still open research. Maybe the sig and def idea is not like that good. Maybe it's not refined enough, and we'll find it out. But it is definitely currently better than the algorithm we have right now. And that's the thing we're trying to implement. And probably even if def and sig algorithm is not enough, if it's not enough, we'll probably need something even more refined at some point, right? And maybe we won't type check each individual constructor separately. I don't know. So, and the problem is that the current issue with the type checker, where if we split things like this, it might crash. That's why this issue is like a major blocker right now for any further research on the dependency analysis to happen. Because even if the current algorithm we've came up with is not enough, something that will be better will probably be even more refined. So we need to fix this problem first. Checking the type of pi itself requires reducing L, you would have a problem. Yes, but then, then we would have, so for that to happen, we would need to have L in the signature here, so they would become mutually recursive. It's hard for me on the spot to come up with an example where we would need to reduce L here, but maybe it is possible, yes. Rest assured, we'll like try to think of many different ways to break this algorithm once we deal with the type checker crashing problem. All right, any more questions? I hope I answered everyone's questions like fully. If someone wants some clarifications on my answers, I can probably provide them.
Yeah, and you'll be in the ZuriHac channel, right?
Yes, I'll be checking on the ZuriHac channel from time to time, and my colleague Vlad might also come in. I won't promise that, but if he comes in, he also might answer some questions.
Okay, nice. Thank you very much, Artem. Thanks everybody for joining.
Thanks for listening. I hope it was an entertaining talk.